some about Kaskada, which is kind of in this event processing space. That sounds like it's this topic that we're all interested in. And specifically, the idea here is to talk about some challenges kind of with dealing with temporal data or temporal queries, and what we mean by that, and look at how at Kaskada we've been thinking about time, and this way of thinking about it lets us write queries or features using event-based data that have been very difficult, if not impossible, before. I mean, as you're probably all aware, in the last decade, events and event processing have become ubiquitous for many different kinds of analytics, ML, predictive analytics, historic analysis, real-time analysis. And this all kind of started with Apache Kafka, which made it really easy to move huge amounts of events around. Since then, we've seen a lot of different ways of processing streams: Apache Storm, Samza, Apache Flink, Apache Spark, Apache Beam. The list goes on. These started out with relatively low-level APIs and have moved towards supporting SQL on the stream. And it's become common practice to store all of those events as raw data in a data lake so that you can go back and run new queries over events. But with all of these technologies and all these advancements, it's still difficult to write queries over the complete user story or all of the events related to a specific user or project or product. And to kind of understand what we mean when we say that, let's look at an example. So here's just a bunch of events, some events from an imaginary game, and some questions that you might want to answer is what motivates Aaron, that player, or how could we improve Brad's product experience? Or why did the player Carla spend so much on the game? But just looking at these tables of events or data, it's really hard to really understand what's going on and see any of those patterns or answer any of those questions. And yet SQL, the way that we usually write and query data, operates on unordered data, just like this. It's really hard to spot those patterns when we're dealing with this disorganized data. So what happens if instead we looked at the entire user story rather than just these four relations? If we just organize it, and here all that means is that we've ordered the events by time and we put all of the events for each user into a single sequence. It becomes much easier to just look at the sequence of events and say, well, Aaron sends out messages after he wins. Maybe he's bragging to his friends, or we see, Brad struggled with the game and probably gave up. It hasn't been playing recently. Carla, the purchases that she made came after a sequence of game overs, a sequence of losses. So maybe when she gets frustrated, she'll make purchases. So all we did was look at the data differently, and it became much easier to see these patterns. And once we've seen these patterns, it becomes much easier to act on them. We could send Brad some tips for how to play and ask him to, re-engage. We could make sure that we don't make the game too easy for Carla so that she stops having to make purchases, but we also don't want to make it too hard. It has to be, something that she wants to keep playing. In the world of event processing and streaming data, this relation, this unordered data has been holding us back. And so if we look further at some of the things that we did to see these patterns, we see that the order of events was critical. Seeing that a purchase happens after a sequence of losses. Seeing that there's time without events, with no activity from some user was important. And working with multiple types of events is essential. We didn't just ask about just the losses or just the wins. We looked at all of the events together. And so these kinds of requirements, these kinds of questions is what led to Kaskada introducing this new concept of a timeline. If a relation is for unordered data, then a timeline is about putting it all in context and understanding that entire temporal context. So it's been said a lot by others And we'll probably mention it a few times, but we really believe here that abstractions matter. The way we think about things matters. They're going to affect how we can think about the problems, how we can express the queries, and how we execute those queries. So we've already seen this idea of a timeline. It was, the previous slide, once I just organized all the data. And all it does is take our data and order it by time and group it by entity. And we saw how much easier it is to understand events when we organize them like that. So all I've done here is move from those kind of hand-drawn or custom ways of viewing it to a more generated way. And now we're using some e-commerce data. So purchases made by these two users, Ben and Davor. And we see here, that they've made some purchases over time, each of them making purchases, different amounts of items purchased. But timelines don't capture just events. At any given time, we might want to ask, how much has each user spent so far? So this answer kind of operates on one timeline and produces a new timeline. So the result here is what we would call a continuous timeline. So it's this cumulative aggregation that shows how each of those users' total purchases evolve over time as they make purchases. In comparison, we call that original timeline that we saw discrete. And what this enables is really powerful because it lets these queries be timelines all the way down. We can start with input events or just input facts that we know to be true, what state each user is in. And both of those can be represented as discrete or continuous timelines. And it retains all of that information from the stream, both the values that are inside the events, as well as what we'll call kind of this temporal context, the time in between events or the other events that are happening nearby. And it does that without losing any of that kind of timing information. And so when we write queries, they operate on timelines. We kind of saw a simple one doing that cumulative aggregation. And then once we're done, we can output the resulting timeline to a stream or a table or to whatever system we need. And one of the interesting things about this is that we can actually output the timeline in different ways. We can get the complete history to understand how values have changed over time. For instance, if we're going to train an ML model on values from the past. Or we can just get a snapshot at a specific point in time. For instance, now, if we're just trying to drive a leaderboard or something like that. So to kind of understand those two different ways of outputting things, let's go back to this aggregation, this timeline that we were looking at. And we can say, well, if we just take all of the points that make up that timeline, every point that aggregation changed, we can just see this as kind of a history. It looks kind of like change data capture, if you're familiar with databases. And that history is enough to reconstruct the timeline in any system. We could be writing this to a key value store if we were materializing it for serving. We could just archive it if we wanted to be able to reconstruct the values at any point in time. And then the other way we can look at it is we can pick a point in time and we can just look at what is the value of each user or each entity at that point in time. So the benefit here is that when you run the query, you get to choose which of these outputs you want. You don't have to think about, am I writing a historic query or a snapshot while you're writing it? And we often find that this was really useful because the same query might be used for training on historic data and then applying a model on the latest data. So being able to get both from one query is really useful. So far we've just looked at this abstraction, timelines. It's just this way of visualizing things, ways of thinking about the problem that's pretty intuitive, right? If I had asked you, how would you draw a timeline in the beginning, you probably would have drawn them similarly. And it captures both the information in those events and the time between them. So instead of having to contort relations, this abstraction from SQL to account for time, you can just focus on getting things done. But of course, that's the important part. How do we actually query with timelines? What can we get done with them? So in this section, I'm just going to talk through a few of the kind of simple queries that just show how they look. So we talked about this basic aggregation. We've seen this earlier. We want to talk about how much did each user spend. So this is just a simple aggregation. You can do something like this in SQL with windowing and cumulative aggregations. You could also do something similar in even Excel, just having the rows and doing cumulative aggregation. And what we see is that using Kaskada or timelines, there's these two ways of writing it. The first one makes it look a lot like a SQL aggregation, and it is, beyond being cumulative. But the second one is one that we've started to find is really nice as we try to compose larger queries. And it kind of tends to emphasize how we think about kind of building up this sequence of computation. So we start out with the purchases amount and we pipe that to the sum aggregation. And we'll see that that pipe syntax is useful for just kind of thinking about this as a building up a sequence of steps. So the previous one was the cumulative sum of all of the purchases, but maybe you're not interested in every purchase made. Maybe you just want to know the purchases made this month. So since the start of this month, it's still a cumulative aggregation. At the start of the month, nobody has made any purchases. And then as I make purchases during the month, my sum that month, so far that month goes up. This is kind of like month to date. And because Kaskada was designed around time and to make windowing and things like that really easy, it shouldn't come as much of a surprise that doing that kind of aggregation is also easy. Again, here I'm showing the pipe syntax. This works with the other syntax as well. But you just say, I want to do that aggregation, but I also want it to be windowed since the beginning of each month. But of course, where this starts to become really powerful is that you're not limited to just windowing based on times like daily or monthly. You can easily window based on other events. An example here would be like, this starts to become kind of data dependent windowing or looking at properties of one event to determine the window around other events. It could be session windows if you log in or log out. Or it could just be, like how many times here. The question is, how many times has a user viewed pages between making purchases? So since the last purchase. The idea here might be that it identifies users who are shopping, they're actively looking to make a purchase, they're looking at items. So here we see when a page view happens, the count of page views that have been made increases. This is the cumulative value that we expect. And when a purchase is made, the cumulative value kind of gets reset. The count goes back to 0. So this kind of matches what we'd expect. And the nice thing is that we can see this is just as easy as what we did with, kind of calendar windows. We just say, now we want a window since the purchase was made. But going back to what we said were some of the things that we needed to do in the beginning, this is using multiple types of events, page views and purchases together to define the result. This is looking at how those page views occurred relative to the other purchases. And expressing this kind of behavior without, kind of this timeline concept or these understanding of timelines can actually be pretty difficult. So here's that same query expressed with SQL. It's long, hard to understand, and I'd say pretty brittle. I'll also be honest, it's full of a lot of tricks. And I didn't really know all of these going in or how to put them all together. I did have to kind of use some help to look up all of these. But at a high level, we take our two tables or our two kinds of events, page views and purchases, and we need to get those into a single thing to operate on. So we have to union them together. Then we have to do this windowed aggregation to compute the cumulative purchases over that union. And then we need to do another windowed aggregation, this time partitioned by the entity and purchase count to kind of fake this resetting whenever a new purchase happens. And all of these tricks, or the need for them, is kind of the cost of this mismatch between the unordered relational abstraction and kind of the fact that we're trying to solve problems working with time. And this cost only grows more out of control as the question becomes more complex. If we come back to timelines and look at one more query, there's a lot more than just improved windowing operations. So far, we've seen how kind of a single computation can change over time, but it also lets us work with values in specific points in time. So here, maybe you don't care about how the page view changes between purchases. Maybe you just care to know the value at the time of each purchase. Kaskada's query language also lets you filter to specific points in time. So here we take that cumulative aggregation, the count of page views between purchase or since the last purchase, and we observe it just when a purchase is made. So when purchases are being made. And then we can continue going. We can take that value that we've made, which is now the count of page views since the last purchase at the time of each purchase, and we can take the average of that. So now we're saying, what is the average number of page views each user makes before they make their next purchase? And we're computing that over time for each user. And we see here that all we need to do is just add another aggregation on the sequence, because all of these aggregations operate on timelines. They take a timeline and produce a timeline. It's very easy for us to stack up a sequence of relatively sophisticated aggregations. Doing this in SQL would require, an additional nested subquery, because you'd have to, first compute the count, then you'd have to compute the mean. But it's really easy when you write it out using the right abstractions to see the flow, right? I'm going to count the page views since the last purchase. I'm going to filter that to when a purchase is made, and then I'm going to compute the average. It's easy to understand. It's easy to change and maintain if you need to. So, but before we kind of move on, I want to look at one other feature of kind of temporal queries, and this is what it means to do a join when you're dealing with timelines. So here we're going to try to answer, what is the average product review at the time of each purchase? And so this one's interesting, because you can imagine that as reviews are made, the review scores associated with an item change. And if what we're trying to understand is maybe the user Ben only makes purchases if the item is reviewed at 4 or more stars, you don't want to know, does the item have 4 or more stars today? You want to know, do these items have 4 or more stars when Ben was making the purchases? So here we're going to start with our review scores by item, but in our original data, maybe they were associated with users still. So we need to first take the review scores and change how they're grouped, or change them to be associated with the items. And then we can just apply an aggregation to compute their mean. But then we can come back to our individual purchases made by Ben and Davor here, and we can ask ourselves, what was the average review score of the item that Davor just purchased, or the item that Ben just purchased? And so we see here that, well, let's see, where's a good example point today? That like the first time Ben purchases a gear, no, never mind. I thought I had a better example point on this, but I don't. So we see here that when Ben makes a purchase of a gear, we take the value from the gear up above and we pull it down and we say, okay, well, the average review score for gears is 2.5. So the average review score for gears when Ben made that purchase was 2.5. And of course, that could be further aggregated, as we've seen before, if you want to take the min or the max or the mean. And all we did here is that we said, okay, first compute that average review score by item, and then look up the items being purchased. So use lookup. It's kind of a join that does a join as of that point in time. But this concept is really useful. It allows you to kind of put results for one user into the context of a bigger picture. So you could imagine that, you first compute some average information about each state, and then you're looking up those aggregates on a per user basis. Working across entities or a different entity allows you to develop an understanding of how those values relate to that larger context and normalize across that population. Flipping back to SQL, we see again, such a query is pretty complicated to express. Some systems have an as of join, which makes this simpler. It's still a little bit more complicated. But The other way of doing this is you kind of create this spline or this table that lets you look up for the time a purchase is made, what is the most recent review made before that? And then for that review, you can do a cumulative average. I'm not going to dig too deeply into this. The point is SQL is much harder to maintain and kind of evolve as we need to. But if we zoom out and look at some bigger examples, one of the things we did was look at some like machine learning notebooks for defining machine learning features for churn prediction. So these were expressed using timeline, or originally expressed using Spark SQL, I believe. And that was like a 63 pages inside of a Jupyter notebook, walking through all of this code to kind of get the data into the right shapes, do the right joins and queries and things like that. Doing the same thing using timelines and kind of the specialization for temporal queries took that 63 pages down to about 2 pages of queries. It eliminated a bunch of those tricks. It made the queries much easier to read and understand what was going on. And so the big point here is that all of these tricks are why even a simple temporal query is going to be difficult to do using SQL. And kind of what our opinion is at Kaskada and what we've built, the whole idea here is that you shouldn't be limited by the abstraction. If you have to come up with a bunch of tricks to express your query, you might do it. You might just change the question. And that's really not that good. So expressing that question shouldn't stand in the way of you asking the right questions. And that's kind of why we wanted to build Kaskada, the system that's designed around answering these temporal questions for you. This is kind of the final piece. It's great. We saw this timeline abstraction, this better way to understand and picture time. We saw it's pretty easy to write some interesting temporal queries using timelines. But of course, that's not that useful if we can't answer those questions. And so this is really where the Kaskada open source project fits. The high level picture here is Kaskada executes temporal queries efficiently. We've seen millions of events per second being processed on my laptop, which is great. It means that you can go get started writing and executing temporal queries on your data without having to go install and configure and manage a distributed system. The key to this efficient execution is kind of really specializing on the timeline abstraction and the properties of temporal queries. At the lowest level, we use Apache Arrow, which provides efficient columnar computations that in many cases can be vectorized either on the CPU or not. At the next level up, we leverage this inherent ordering by time and this partitioning by entity that's present in timelines. Every operation is aware of that, preserves that property, and takes advantage of that property. And finally, at the highest level, we support this incremental execution, so you can choose how often to update results. So kind of when you're running on a stream and new data is pouring in, you can choose to run as soon as a new batch arrives. You can choose to update your results once an hour. And it's really up to you, kind of depending on how you want to balance latency and the cost of kind of maintaining those values. As a really rough benchmarks, some rough numbers, we ran some of those queries that we showed, with Kaskada using timeline and with the SQL variants using like as of join for the temporal join case in DuckDB, which is a really easy to set up and install local SQL engine on a bunch of Parquet files. So these had about 50 million page views, 10 million purchases. We're not huge data, but multiple gigabytes. And what we saw is that on kind of simple queries where order didn't really matter, you just wanted the snapshot. As expected, DuckDB does better. But most of those queries were just a few seconds in either system. But when we started to get to these temporal queries, these kinds of queries that Kaskada is designed for, data-dependent windowing, like we looked at. So how many page views have I made since the last purchase? What is the average of that? Or temporal join. We start to see that Kaskada starts to pull ahead by taking advantage of that ordering and those assumptions that timelines allow it to take. We have a bunch of plans for further significant improvements. We haven't spent a ton of time on performance optimization. Currently, we don't do much to take advantage of partitioning and multiple threads. So we expect these numbers to only get better over time. So Kaskada is open source, it's under active development. So it provides this timeline-based query language, this efficient query engine built on Apache Arrow. And you can go get it, give it a try today. It's got a bunch of nice things and it's only going to keep improving. And kind of finally at the end, to better understand the needs of these open source users, we are doing some kind of hands-on workshops where it'll, you'll be able to ask questions and talk to one of us. Sign up now if you want to get some more hands-on experience with these temporal queries in a small group. The space is limited, so sign up now if you're interested. And we're working to kind of build this open source community. So if you have temporal questions, it would be great if you can give it a try and let us know how it goes. And if you're interested in these kinds of problems, we'd love it if you could come and talk to us. There's a link on that community page to join our Slack. Thanks.
Thank you. Great talk, and it looks really cool. So I got some very naive questions since I don't know your product at all. So is it like a service? Is it an engine? Is it a library? So what it looks like?
Great question. So right now, the most common usage is as just like a binary that you can download and run. And then there's kind of a Python client that can talk to that so that you can write queries in like Jupyter notebooks as well.
I see.
There is work being done on one direction to kind of put it behind a service and make it available in that way for people who prefer that. We're also looking at being able to kind of take that binary and use it more as like a library on top of Apache Spark, Apache Flink, or Apache Beam as kind of a way of operating on existing distributed systems.
I see.
Depending on kind of what people are interested in.
So just as in the first scenarios, you're saying that it's something you run. So the data, like for example, for most of the data, especially the large data, is on cloud, is our data lake, S3, Parquet, and all that sort of thing. So we basically, it's like a agent, access the data directly, is running a laptop, or
for the benchmarks against DuckDB, since that one also runs locally, I just had the Parquet files on my disk. So it was in both cases reading directly. But the binary that represents Kaskada can support reading Parquet files from various clouds like S3 and GCP, etc. And there's also ongoing work to kind of support Pulsar and streaming formats.
Got it. Okay, so the next question related to how this thing works. And so maybe I probably didn't quite fully understand yet. So the syntax you express the simple things, I assume like either they are kind of a representation of the table or kind of an event like a purchase, a view, those kind of equivalent already streamlined through the timeline. So if the original data itself is not, basically it's a bit structure by user, by, whatever, it's not really streamlined through the timeline. So based on your diagram, it sounds like you have to essentially do the SQL join before you do this, because you have to you put the timeline together if the original table doesn't. Essentially, in other words, you had to do a join before.
Yes.
So you do a fair comparison, the left and the right.
So there are joins. In general, the only thing that we currently do in kind of this prepare phase or this ahead of time phase is ordering the data, which on the one hand, it's something that we kind of do ahead of time, but many existing data lakes already kind of sort and partition their data when, like if you look at Apache Iceberg and things like that, the Parquet files are often already ordered. Similarly, I think, if you're reading from a stream, modulo some amount of late data, things are mostly in order. So kind of ordering is available. And then the other piece, there is a join, but when we currently read, we do a merge while we're running the query. So basically we have a Parquet file for each type of event, or so for each kind of primitive stream, and then we can merge those based on order. So it's more like a merge join from a database than like a full kind of hash join or anything like that.
my comparison coming from, say, if you do that prep work, maybe you should compare with the table which you already ordered by the timeline, and then the query won't be as complex as the one you show on the right-hand side, right? Because the 1 year order.
So the query complexity would still be largely the same, because in order for like SQL to know that you want the kind of cumulative the windows to be cumulative and ordered by time, you would still need to say ordered by time. I think you're likely right that the performance might be different if the SQL engine knew that the inputs were already ordered. One of the things that we've seen here is that a lot of SQL engines have varying degrees of optimizing for that case. You know, they tend to focus on the more general cases and really tune like hash join, rather than kind of detecting the more complicated cases, which might be harder for them to see, where, okay, all the inputs are ordered. Oh, I need to do this ordered output. Okay, maybe I can do a merge join. So it's possible that the SQL would be about as complicated, but that the query would run faster if it knew it was ordered. But many engines don't take advantage of that as well as they could. You know, not they can't, is just kind of outside their focus.
Yeah, makes sense. I have one last question. I know there's several questions people posting on the chat already. The people using SQL because you know, they already know SQL. They've been doing SQL for years and 30, 40 years. So there's plenty of the syntax. So whether your new syntax is concise and is much shorter, but people have to learn. So that's the trade-off. You basically say, hey, learning my new thing.
Yeah, I mean, it is. And, you know, we've looked at kind of ways that we could use SQL. You know, it tends to have a lot of limitations around kind of windowing and things like that. We have talked to people and kind of done user studies on you know, how difficult it is to learn, and generally we hear that it's not a huge problem. One way to think about it is that the syntax is largely SQL, right? Like things that you would do inside of SQL in terms of aggregations are what you would do inside of Kaskada. And then kind of the bigger differences are, you know, you have a few other operations like lookup, but you can kind of understand that as in join, and it's not as different from SQL as it might seem.
Well, of course, if you know it, I wouldn't think about a lookup is going to be a join. But anyway, so let's look at the question. Noel, hope I pronounced your name right. Noel, is there an easy way to write tests for queries?
I mean, not at the time. Internally, we have a ton of integration tests that kind of use CSV or JSON, you know, in like 10 rows in each table. And, you know, you can write that, and that could be something that we could break out as part of the open source project. But otherwise, you know, you can just run the query on some data and see what it produces.
Yeah, he also asks, it sounds like a DB would have to be exported to a Parquet file if it is not already available in Parquet file format. What other formats are supported?
Yeah, great question. So currently for kind of file formats, so like, you know, file sitting on an object store somewhere, CSV and Parquet are supported. I think it would be pretty easy. The Apache Arrow library that we use also supports JSON. It's like an array of JSON records. We are also working on Apache Pulsar integrations. So something, a bunch of rows coming in on a stream using Avro. And I think that in general, many systems already support Parquet files. Like we've looked at Iceberg. And I want to say Delta Lake uses Parquet files under the hood. So in the big data space, kind of having data already in Parquet files is pretty common. And, you know, for other cases, we are interested in kind of extending the system. That's part of the, you know, benefits of open source and kind of having these conversations about what else people might want.
Yeah, most people using Parquet. I think there's an ORC as well, but majority of them are Parquet. And Parquet and with Iceberg, with Hootie, or with Delta Lake. Let me see. Wansha asking, how does Kaskada fit into the architecture of streaming processing frameworks, such as Spark, Flink, and Beam, etc.?
Yeah, I mean, that's a great question. And actually, it's one that we're just starting to explore. So it's kind of, I said when Chester asked earlier, currently, Kaskada, runs as a binary. It tends to run all in one machine, which often is really good for, many kind of medium data problems, which many of us actually have, can be done really quickly on modern machines, passing things around in memory. You never need to kind of deal with shuffles and things like that. But there are still a ton of these distributed data frameworks, and there are distributed data problems that do really need a bunch of machines like Spark, Flink, and Beam. And so kind of we recently sent a proposal to the Apache Beam list on kind of how this could work. And the way to think about it is that inside of your Beam or Spark or Flink pipeline, you can use Kaskada to express some transformation on one or more kind of collections or RDDs or whatever the stream framework of your choice calls them. So kind of each table or stream would be like a P collection or an RDD. And you can write a query over one or more of those, and that'll produce the rows that come out of that query. So basically, you can embed it into Spark or Flink or Beam. Under the hood, that could be compiled down into a Kaskada execution plan and kind of turned into something that on like Spark or Flink would say, okay, well, I need to do these 5 things using Kaskada. So I'm going to take that batch of data, run Kaskada on, or have Kaskada process that, get a new batch. And then, okay, now I have to shuffle it. So kind of using Spark or Flink to take care of the shuffle and the distributed orchestration, and using Kaskada to implement the logic on the batches. There's a project that we've looked at that does this for Spark using data fusion, which is basically like an Apache Arrow-based SQL engine, which does kind of a very similar fit for kind of how they operate on batches inside of the distributed framework. Does that kind of answer the question?
I think it does. I know the data fusion. I think from Andy Moore. I think that's his name. So he's working from NVIDIA. So
question. So
sorry, go ahead. Yes, Ali.
Oh yeah, I'm still a little confused. What exactly is Kaskada? I understand there's some storage components based on Arrow, and there is some query language that probably needs to be parsed. But fundamentally, is there some indexing happening? Is there some compute layer that is doing streaming, or do you just run on top of?
I mean,
other platforms?
mostly it's actually compute. So Apache Arrow, I like to think of Apache Arrow as a compute layer or a component of a compute layer, right? So the way that I would think about it is that if Apache Parquet is columnar storage on disk, then Apache Arrow is columnar storage in memory. And so it basically defines this in-memory representation, which is columnar in the same way that Parquet stores on disk or similar to that, and a bunch of operations on that. So kind of taking advantage of columnar processing, which tends to have a lot better CPU performance and vectorization opportunities.
So you're saying Arrow has an embedded operator list available that you're essentially extending?
It has like an embedded operator list, and you can build more. So Arrow itself is more about the representation, and then as part of that representation, they provide some kind of common operations, and then you can build your own operations on top of it.
And then you talked about stream processing, including ability to tune the freshness. Who's executing this stream processing job continuously? Is it some external stream processor, or is it something inside Kaskada?
So currently we support multiple ways of doing this. So one way of doing this is kind of the incremental processing that I mentioned, where you run Kaskada on the current set of data, it produces a checkpoint and the results, and then you can run it again as new data has arrived, and that can kind of let you choose how often you want to update the results. We're also currently working on consuming straight from Pulsar and kind of having that be an ongoing process that just Kaskada runs basically in a loop, pulling data from Pulsar, updating the materializations wherever you ask them to be written to, and that could be deployed to like Kubernetes or something like that to keep it running.
Okay.
Okay, next question actually also coming from Wang Xia. He said it's a Kaskada suitable for second level real-time event processing or more suitable for the hours level batch processing. It's kind of like if you paraphrase this, I think is this a micro batch or is it real time?
Yeah, I mean, I think it's suitable for both. I think, like significantly sub-second, like when you start to talk about closer to milliseconds, like true real time, it probably wouldn't be a great fit. For kind of streaming real time or like, maybe second level, it could probably be a pretty good fit. Obviously, it starts to be about kind of efficiency or kind of what's most efficient, right? If you have an arrow batch is kind of columnar representation and you have a bunch of one row things, there's going to be some overhead there, and it becomes a lot more efficient if you can have like 100,000 rows being processed at a time. But it's still efficient enough that you could do 1 or 10 rows and kind of be at that second level. So kind of we've used it in both. And certainly, like, if you only have a small number of events per second, then that overhead is going to be less concerning. So I think that second level and hour level, we've used it for both, and it works pretty well in both of those cases. But kind of millisecond level, you would probably want to do something different.
I see. For those for audiences, so even though you can type a question in the chat, since we don't have a lot of people, you can unmute yourself and just ask a question directly if you want to. So follow the streaming question. So you mentioned that it can be using for streaming pipelines. So like, for example, for most of the Spark, just for example, the pipeline most of it probably written in Scala and others in Python. And I know Kaskada is written in Rust. So you have the different language bindings for your library?
We don't currently, as part of what we're working on developing for the Beam support, which could, Beam can run on Spark. So actually, once we have the Beam support, it would potentially support running just Kaskada on Spark, kind of via Beam as an intermediary. The way that I guess I would explain that is like, think about the elements that Spark would be operating on at that point would be a batch of records. So we use Apache Arrow to represent kind of a batch, and that could be a small batch of like 1 row, or it could be 100,000 rows. And then when it hands off to Kaskada, it would be saying like, process this batch. It would be, but I think what Spark does for Python UDF actually is that it uses Arrow under the hood. So that instead of passing 1 row at a time between the JVM and Python, it can pass 100,000 rows and then run a pandas operation on it. So kind of Apache Arrow is already used as an interchange there. And that would kind of be the layer of interchange that we would be using as well.
So it's very similar to the Spark macro batching, not the structure streaming, like a macro batch, the old version of the, like every couple of minutes, your pull, you get a batch in a process. Sort of like that.
In similarity, yeah. I guess I would say you can do micro batch and pull batches every millisecond or every second, right? And in practice, like many systems, like Flink, I believe, will actually, see how many messages are built up. Well, it was processing the previous chunk and then process multiple messages at a time, right? So I think that there's a lot of fuzziness when we talk about like micro batch versus really row at a time.
I see.
So yeah, yes, but I would say that it's not like micro batch pulling batches once per minute. It's more like pull off a batch of what's arrived since the last time, process it, then pull off the next batch. At which point there's very little difference between processing 1 row at a time versus processing a row at a time.
So back to the other one. So you mentioned that you will have, once you have a Beam support, you can support different, language bindings. Beam is essentially using protobuf to kind of generating the different stubs for different languages. So you basically go through that route, right?
Mm-hmm.
Okay, got it. Okay, any other questions from the audience, please? So if no more questions, I want to thank Ben again. Apologize for beginning for the mess up on the URL.
No worries.
So, thank you so much. And that concludes talk for today. So if you're interested in streaming related topic, please watch it for September 27th event, which will have 2 streaming talks from the creator of Apache Flink. So until now, for now, thank you for your coming, and we'll see you next time. Okay, bye-bye.
I guess I've got a question now.
Oh, you do? Okay, all right.
Do the events have to come in order, and can the events come with their own timestamps, or does the timestamp be assigned as when the event came?
So what you're asking about is kind of like late data. Does it handle that? Because you can always use stream order, and then that gives you an order. So yeah, it can do that. The way that we're kind of doing that under the hood is, there's various techniques you can do, kind of like Slack buffers, where you kind of buffer some events until you believe it's not there. There's watermarking, like Beam introduced, or maybe Millwheel introduced it, and Beam and Spark and Flink all kind of do some form of watermarking these days. We're basically, you look ahead and you take advantage of the fact that, yeah, you might get events that are out of order, but you will rarely get them, significantly out of order. So you kind of build up a buffer, and you're looking at kind of this watermark, this notion of how much out of orderness you expect to see, and you're kind of processing them there. One of the things that I think is really novel or kind of interesting about the Kaskada is that using that incremental approach we talked about, it'll actually drop checkpoints, like let's say every 10 minutes of event time, and it can just keep processing. And if it, under this assumption, it's optimistic assumption that things are in order. It's kind of like, optimistic concurrency almost. It's just assume things are in order. But if you're dropping a checkpoint every 10 minutes and you reach an event where it is out of order, you can actually just kind of say, okay, well, if I go back to an earlier checkpoint, and then I can process the stuff that happened after that checkpoint in this new order that I've discovered. So basically, you don't need to choose between delaying your processing until you've seen this watermark, this idea that things are going to be in order, and just kind of throwing away the out of order data that some systems do. You can kind of say, well, let's run as fast as I can, assuming it's all in order. And then if I'm ever wrong, I can just hop back to before I, made the mistake and assumed that I wasn't going to see anything here, and incorporate that late element. So it actually does support event time as well as stream time. Yeah.
Okay.